Okay, so we continue talking about NIST document, special publication, network of things. So there they actually talk about 5 primitives. We talk about sensors. So the second primitive is aggregator. An aggregator is a software implementation based on mathematical functions that transforms group of raw data into intermediate or aggregated data. Raw data can come from any source, it can be even a telescope or something, because we are collecting many different types of data. Aggregators help in managing big data. Basic properties, assumptions, recommendations, and general statements about aggregators include: aggregators may be virtual due to the benefit of changing implementations quickly and increased malleability. A situation may exist where aggregators are physically manufactured, for example, a field programmable gateway or hard-coded aggregator that is not programmable. Aggregators may also act in a similar way as n-version voters. So n-version voter is actually a term in computer science. So think about all of you implementing an algorithm, right? And which we will do. I will give an homework. So for instance, you will implement a block cipher. And it will all work in the same way, right? But all of your implementation will be different. So this is like n-version voter, and different thing working in the same way. Aggregators require computing horsepower. However, this assumption can be relaxed by changing the definition and assumption of virtual to physical. For example, firmware, microcontroller, or microprocessor. And for example, aggregators could execute on faster hardware such as a smartphone. Aggregators will likely use weights to compute intermediate aggregated data. So sometimes people talk about Internet of Things, and as sensors, instead of using a small device, they use something like Raspberry Pi, but it is not that a small device. You can use it as an aggregator, but saying that it is a small device and use it as a sensor actually kind of violates this definition. Aggregators have two actors for consolidating large volumes of data into lesser amounts: clusters and weights. So these are two sub-primitives we are going to talk about. They are really important. Aggregators process big data concerns within network of things, and to satisfy this role, computational performance enhancing technologies will be needed. This is the only primitive with actors. So sensors may communicate directly with other sensors and thus act in some situations quite similar to aggregators. So if your sensor is capable enough, then they can do this. But generally, if they have limited power, they simply transfer data they receive to the aggregator. They don't work on the data itself. Intermediate aggregated data may suffer from some level of information loss. Proper care in the aggregation process should be given to significant digits, rounding, averaging, and other arithmetic operations to avoid unnecessary loss of precision. Precision is really important still, when we first learn programming, especially when at the time the bits reserved for the precision was really low. So you could easily see the precision loss. But in these devices, this still applies. Maybe they are working on just a few bits of information. So a single precision loss might be important. So it should be really considered. For each cluster, there should be an aggregator or set of potential aggregators. Aggregators are executed at a specific time and for a fixed time interval or event-driven. Aggregators may be acquired off the shelf. Note that aggregators may be non-existent and will need to be homegrown. This may create a problem for huge volumes of data within a network of things. Some network of things may not have an aggregator. For example, a single light sensor will send a signal directly to a smart light bulb to turn it off and on, right? So you don't need an aggregator all the time. But of course, some companies prefer to send that data to a gateway than to your mobile phone so that you can communicate with all of the devices using the gateway. Security is a concern for aggregators, malware or general defects, and for the sensitivity of their aggregated data. Further, aggregators could be attacked, for example, by denying them the ability to operate, execute, or by feeding them bogus data. So this is really important, and if you keep feeding data in a fast way, you also create a denial of service attack, right? So security is really a huge concern. This is one of the parts that we are going to focus in our course. Of course, reliability is a concern for aggregators. General defects can cause a problem. So we said that it actually has two actors. First one is sensor cluster. The second is weight. So let's start with sensor cluster. A cluster is an abstract grouping of sensors that can appear and disappear instantaneously. Basic properties, assumptions, recommendations, and general statements about clusters include: clusters are abstractions of a set of sensors along with the data they output. Clusters may be created in an ad hoc manner or organized according to fixed rules. And although you create a cluster, you may add or remove any sensor at any time, right? Clusters are not inherently physical. So here are some notations. CI is essentially a cluster of the sensor data from N sensors, like D1 to Dn. CI may share one or more sensors with CK, a different cluster, or with other network of things. This is somewhat important because competing organizations may be receiving data that they believe to be unique and purposed only for them to receive, and not realizing a competitor is also receiving the same sensor data, right? And this happens actually most of the time. Continuous binding of a sensor to a cluster may result in little ability to mitigate trustworthiness concerns of a real-time network of things if the binding occurs late. Clusters are malleable and can change their collection of sensors and their data at any time. The composition of clusters is dependent on what mechanisms is employed to aggregate the data, which ultimately impacts the purpose and requirement of a specific network of things. So yeah, this is what we talk about clusters. So the second thing is weight, second actor in this second primitive. Weight is the degree to which a particular sensor's data will impact an aggregator's computation. Okay? A weight may be hardwired or modified on the fly. A weight may be based on a sensor's perceived trustworthiness. For example, based on who is the sensor's owner, manufacturer, geographic location, where the sensor is operating, sensor's age or version, previous failures or partial failures of sensor, sensor tampering, sensor delays in returning data, etc. So as you can see, hereby we are actually focusing on this. So if you have 10 sensors, you may believe them they're identical. So you weight them equally, okay? All of their data are the same to you. So you don't favor one of it. But here we are saying that maybe one of them is old, or maybe one of them is in a condition which affects its sensing ability. So you cannot always assume that all of the sensors are identical and give same importance to each data. Okay, so maybe one of your sensors are from a manufacturer and they build a good device, and maybe a second sensor is really bad. So this is why you have to determine a way to measure this data. Different network of things may leverage the same sensor data and recalibrate the weights per the purpose of a specific network of things. It is not implied that an aggregator is necessarily a functional linear combination of sensor outputs. This is what I meant actually. Weights could be based on other logical insights such as the following. If sensor A output is greater than 1, use sensor B, output as use sensor C's output. So as you can see, you don't need to focus all of them and just sum them and take the average of it as the weight. Aggregators may employ artificial intelligence techniques to modify their clusters and weights on the fly. So this way, in order to increase the reliability of the data, maybe you can use AI techniques to modify the weights. Weights will affect the degree of information loss during the creation of intermediate data. Redundant sensors may increase a sensor's weight if a grouping of redundant sensor data is in agreement and procedures the same result. Repeated sampling of the same sensor might also affect a sensor's weighting, either positively or negatively, depending on the continuity of a particular output value during a fixed time interval. Security concerns for weights is related to possible tampering of the weights. The appropriateness, in other words, correctness of weights is crucial for the purpose of a network of things. A simple aggregator might implement the summation, sum all of the values, then divide by x, where x is the number of data points, and where the weight for each data point is uniform. So this is what I meant initially. So if you think them there, give you the data and you trust them in the same way, then this is the basic thing you can do. But most of the time, you have to create the weights in a better way.